Kousik Deb. Good afternoon, Professor.
Good afternoon.
Yeah. Just 1 minute. So, how are you, sir? How are you? I am Dr. D.L. Venkatesh Babu, calling from Bangalore. Thank you very much. We are very much happy and honored to have you today.
Thank you very much for this invitation.
A lot of professionals joined. They are awaiting for your, because we have circulated all consulting engineers of Bangalore. A lot of professionals joined. And also YouTube link also we created to get the benefit of outside also. Throughout India, there is a representation. We'll start the meeting once the strength is assembled, sir.
Okay, no problem.
Yes, sir. Thank you, sir. Mr. Sanat. You are admitting? You are admitting?
Yes, sir. Yes, sir.
Yeah. As Dr. Suravi is there? Dr. Suravi?
Yes, sir.
Yes, sir.
Yeah, please.
We can start, sir.
Yeah. See, good afternoon to another present. We are very happy and honored to have Professor Kousik D, Associate Professor, Civil Engineering Department, IIT Kharagpur, West Bengal. He is giving a lecture or a webinar on stone column, improved ground and recent advances. Sir, we are very much honored with your presence and also sharing your sparing your valuable time with us to share. This is the advanced topic to all of us. On behalf of Nagarjuna College of Engineering Technology and my department and my own, I welcome you, sir, wholeheartedly for this webinar. And also, I'm very happy to welcome all the delegates across India, and you have shown good response to learn something about the stone column, improved ground, recent advances topic. Thank you all for joining, all the consulting engineers and professors and faculty members and my dear students. Thank you for joining and supporting all our webinars. This is almost another 2 webinars is there. We have scheduled a series of webinar to learn behind the curriculum. I'll thank you all once again for supporting this. And also I welcome all of you. And also we welcome, and also first let me thank to our management, Nagarjuna College of Engineering Technology, and my principal giving the permission to host a series of webinars in order to improve our knowledge levels, what the industry expects. I request the coordinator of the webinar, Dr. Suravi Pal, Associate Professor, Nagarjuna College of Engineering Technology. Please introduce the guest speaker of the webinar. Dr. Suravi?
Yes, sir. Sure, sir.
Please introduce the chief guest.
Yes, sure, sir. Good afternoon and welcome everyone. Thank you for joining us today's webinar. My name is Suravi Pal. I am Associate Professor in Civil Engineering Department at Nagarjuna College of Engineering and Technology. Today our webinar topic is Stone Column Improved Ground Recent Advances and will be presented by Dr. Kousik Deb. Let me introduce you to Dr. Kousik Deb and his achievements. He is presently working as Associate Professor in Civil Engineering Department at IIT Kharagpur. He has more than 15 years of research experience in the area of geosynthetic reinforced earth, numerical modeling, ground improvement, soil structure interaction, foundation and embankment on soft soil, and geotechnical earthquake engineering. He has published more than 100 research articles, including about 65 papers in referred journal with an H index of 16 and around 900 citations in Scopus. He visited Germany as a visiting research fellow under that fellowship. He is the recipient of IIT Roorkee Shamshar Prakash Research Award for Outstanding Research Contribution in Geotechnical Engineering by Young Indian Researcher. He has also received the Institution of Engineers Young Engineer Award, Excellent Paper Award to a junior individual given by International Association for Computer Methods and Advances in Geomechanics, USA. Dr. Deb has also selected for Endeavour Research Fellowship to undertake a postdoctoral research program in Australia. Under Dr. Deb's guidance, 6 PhD are awarded and 5 more are in progress. Dr. Deb has completed 2 sponsored research projects funded by DST. He has successfully completed number of consultancy projects. Dr. Deb has offered course on soil structure interaction, advanced foundation engineering, and foundation engineering under NPTEL online certification program. It's my great honor and pleasure to introduce you, sir. So, well, everyone, let's begin with today's session. If anyone have any question, they can ask at the end of the session. So over to you, sir.
Okay, thank you, Dr. Pal and Dr. Babu. And thank you very much for your invitation and give me an opportunity to give a lecture on a topic on stone column improved ground. Mainly, I will concentrate in this lecture that first, what is stone column? And then I will concentrate the recent work that me and my students, basically in my group, which have been done in last 5 or 6 years. And obviously, I will, to continuation on this topic, I will also give some idea what are the previous works and what are the future scope of these works also. So first, if I discuss that what are the problems for foundation on weak and soft soil, because we know when we design a foundation, the major challenges are on this type of soil are the excessive settlement and possible bearing capacity failure, because we know these two are the major design criteria. When you design a foundation, we check the settlement and we check whether soil is able to carry the load which is coming from the superstructure. So, and these type of, if the soil is weak or the poor or soft, so then we have to face these type of problems. The settlement will be very excessive, which is beyond the permissible limit, and the bearing, there will be a possible bearing capacity failure. Now, what are the options? So one option, we can go for the deep foundation and we can avoid this poor soil, and we can go for the foundation. But sometimes we do, but there is an alternate way, which sometimes if these pile foundations are so costly, so we can go for an alternate arrangement that we can improve the ground. So, and that's why this ground improvement concept came. So now when we are talking about the improvements of soil properties, now what are the properties basically we will improve? So basically we will improve the property of compression, consolidation, permeability. So as we know, these properties, if we can improve these properties, so automatically the settlement of the soil or settlement of the foundation will automatically improve, because these first three properties are related to the settlement of the foundation. In addition to, we can improve the strength property of the soil. So the fourth property, that the strength property, that is related to the bearing capacity of the foundation. So now ultimately what we are improving? We are improving the settlement, we are improving the load carrying capacity of the soil, so that we can construct foundation on this poor or the weak soil. Now, there are a number of ways we can improve the soil properties. Basically, we can improve the settlement and the bearing capacity. But today, I will mainly concentrate one of such methods or one of such methodology, because it is not possible to explain all the properties in a short lecture. So I will concentrate one such methods. So there are methods by compaction. We can improve the soil properties. The compaction can be dynamic compaction. It can be blasting also. Now we can provide the vertical drain. So that means in compaction is mainly we provide for granular type of soil, where by compacting we can reduce the void ratio and we can make the soil dense, so that its strength carrying capacity will be improved or load carrying capacity will be improved. We can provide the vertical drain so that it can provide a drainage path, so that we can get a faster degree of consolidation or faster rate of consolidation. So if there is a faster rate of consolidation, so soil can get the strain in a faster rate. So we can provide, we can go for grouting, we can provide, we can add some inclusion also like geosynthetic, soil nail. So there are a lot of options are there. Okay. So, but today I will discuss only the stone column or the vibro replacement. So there are two things. Let me explain what are those two things. One is vibro compaction, one is vibro replacement. So so we can use the vibro float to, first for the vibro compaction, we can vibrate by using the vibro float, and the created portion we can put the sand, and then we can make a dense soil. Initially it was a poor soil, so that we can construct the structure. So this type of vibro compaction is suitable for granular type of soil. So it is not suitable if there is a fines present. How much? Suppose if it is more than 20% fines are present, then this vibro compaction technique will not give a good result. Or other way, if there is a more than 3% clay is there, then also will not get a good result. So if the fine amount is less than 20%, or there's a fine K amount less than 3%, then we can go for the vibro compaction. So the next method is the vibro replacement. So what is the difference between the vibro compaction and the vibro replacement? In the vibro compaction, we are densifying the soil by vibration. In the vibro replacement, we are putting a stiffer material, or we can say stone, within the soil, so that the overall stiffness of the soil will be increased or will be improved. So there are a number of ways we can do that. There are dry method, there are wet method, there are case method. So dry method, wet method, this is a without casing method, but with using the casing also, borehole casing also, we can construct the stone column. So sometimes these stone columns are called the granular piles also. So what we can do? So there is a dry method where we can provide the vibration, and then by these vibration we can the created portion we can place the stone. Okay, and so this wet method. So this dry method is basically suitable for dry soil or sandy soil or unsaturated soil. And if the soil is saturated below water table, then we'll go for the wet method, where we can provide a water jet and created portion is inserted the stone. So that means we can fill those portion by providing the stones. And we can have a case method also. So there are a number of ways we can install the stone column. So, but the dry method, wet method are the most common method. Sometimes we can go for the cased method also. So basically, it's a stone column. So that means it has a length instead of diameter. And within that length and diameter, we provide stones and we place this column with certain spacing. So now when we are talking about the design of stone column, we are talking about what would be the diameter of the column, what would be the spacing between the column, and definitely what would be the length of the column. Okay, there's some other properties also. I will come one by one. So in normal sense, when we are talking about the design, we are talking about the spacing, diameter, and the length. Okay, and then I will come back that how we can design those things. What are the properties are required to design that, and what are the advanced studies that we should incorporate within the design. So now, if I look at this curve, so this is the vibro compaction and this is the vibro replacement. As I mentioned, the vibro compaction is not suitable if there is a fines is present. So that's why, or excessive amount of fines is present. So that's why you can see the vibro compaction can be done for the up to the sand, even not the fine sand. So coarse or medium coarse, we can do it. But vibro replacement, we can do it for silt, we can do it for clay also. So that means in this stone column, we can go for sand, we can go for clay. Now I will discuss when I will use the stone column in clay for what purpose, and when I will use the stone column in the sand for what purpose. So now some properties of the stone column, that typical diameter of the column is generally taken as 0.6 to 1 meter. Okay, so now if the ground is softer, soft clay say, so we have to go for larger diameter, which is expected. Now, typical spacing between the column to column is 1.5 meter to 3 meter. Okay, so these are typical values. And length, we can go up to 20 meters generally, but sometimes if required, we can go up to 30 meter also. And obviously, as your length will increase, your cost will definitely increase. But at normal length, 15 to 20 meter, about up to it has been reported that it has been constructed up to 30 meter also. Now, what is the stone size or the gravel size that is inserted into as a column? So that gravel size is 20 to 75 millimeter. And now, once you construct the stone column, so these columns, over that we have to provide a sand blanket whose thickness is 0.3 meter to 1 meter. Now, what is the purpose of this sand blanket? The purpose of this sand blanket, it will help to distribute the stresses which is coming from the superstructure on the column. And the second one, it will act as a drainage purpose. Okay, so that means it will distribute the stress as well as it will act as a drainage purpose. So that's why providing sand blanket over the column is always recommended. So I will discuss one by one that how it will act as a sand blanket, what is the requirement of the sand blanket to act as a drainage path. Now let's discuss about the possible failure of the column. Okay, so now there are three possible failures of the column. First one, if you see, this is the bulging type of failure. That means when you apply a load on the column, it will bulge. And if there is excessive amount of bulge, then it will fail. And the second type of failure, it is the shear failure. Okay, and third type of failure, it is also a shear failure. It is a punching shear type of failure. So we can say this is punching failure, this is shear failure, second one, and this is bulging failure. Now, when the bulging failure will occur, suppose if the column is a long column. So now what is will treated as a long column? So generally, if the column is more than, as for this figure, it's more than 2 to 3 times of the diameter, then it is expected the bulging failure will occur. But sometimes few researchers have mentioned that it can be go up to 4 to 6D also. So that means in one word, I can say if it is more than 5 or 4, 6D, so definitely there will be bulging failure. And it is the most common failure of the stone column, because most of the cases, column length is more than 6 or 5D. So the bulging failure is the most common type of failure. Now, next one is the shear failure. If it is a short column, that's within, say, 2 to 3D, or sometimes 4 to 5D, but it is resting on a rigid base. So you can see it is a short column resting on a rigid base. So there will be a shear failure. But if it is a short column, but it is not resting on a rigid base, it is a floating type of column, then there will be a punching type of failure. Now, all these 3 types of failure, there are 3 different load carrying capacity methodologies are there. So I will not discuss all these things because these are very common, available for the code also. We have one IS code also. There also you will get these methods. But mostly I will concentrate on the first one, which is more common. Okay. So now in this total discussion, I will mainly concentrate the first type of column, which is a long column. It can be rigid base, it can be floating also, but it's a long column and it will fail in bulging. So other 2 cases I will not discuss. So now this is a typical test photographs. So it is after the test, your slurry is inserted here, plaster of Paris type of material is inserted. Then after the test is done carefully, your stones are removed from the hole, and then that void portion, the plaster of Paris material is inserted, and it is give some time so that it become hard, and after that the clays are removed, and then these final photographs are taken, so that we can study the bulging in better way. So now, as I mentioned, the bulging I'm talking about, that is a single column. Now if it is in a group, you can see that the insert column, inner column has less amount of bulging compared to the outer column. Even outer column also, the outside has more bulging compared to the inner side, which is expected because in the insert one, because we have a soil pressure from both the direction. But in outer column, the soil pressure or the column is bulging in only one direction. So that's why there is more bulging is expected. So this is for the street footing. Similarly, for the circular footing, that means outer portion more bulging, inner portion less bulging. So now, as I discussed that we have to provide a granular pad over the column. So this granular pad will reduce the bulging. You can see that here this is without any granular pad. So this bulging is more, but if you provide the granular pad, bulging will reduce. So why the bulging will reduce? Because it will help to distribute the stresses. Initially, all the stresses will be concentrated on the column. Now, if you provide the sand pad, that will distribute the stresses over this area. So then all the stresses will be distributed. So that will help. How it will help? So suppose, for example, if you apply the stress on this column only, then they will be bulging this side. But now, if you have a granular material and stresses is distributed over there, now the stresses is acting on the column itself, and the stresses is acting outside the column also. Now, this stress which is acting outside the column, that will try to prevent the bulge, because it is giving a stress outside the column, the soil. So that soil also move in the opposite direction or towards the column, because of the bulge, column is moving towards the soil, and as you are making a stress or over the soil, now soil is also trying to move towards the column. So that's why the bulging will be reduced. It will reduce the bulging. So obviously, in such case, it can take more amount of load. So its load carrying capacity will also increase. So that is the advantage of providing the granular pad. It has another use also. It will act as a drainage path, that I will come later on. Now, when you are talking about this stone column, it has some arrangement. So what is the arrangement? You can see it can be, the grid can be in different types. So first grid, it's a triangular grid. You can see it's a triangular grid. So columns are given in triangular way. Okay. Second grid is a rectangular pattern. And third grid is a hexagonal pattern. So now there are different terminology which will be used and which are very common for stone column improved ground. The first terminology that we can go for a unit cell approach. Although I have discussed that the inner column and the outer column may not behave similar way, but when you do the analysis, we take a unit cell approach. Unit cell approach means we take only one particular column and we assume that all the columns will behave similar way. Okay, but which is more or less, this assumption is valid because in the figure I have shown you 2 or 3 columns, but here generally 2-3 columns will not be used at a time. It will be have a huge number. Okay, so hundreds of columns. So after that, say 90% column will behave as the inner column, and the outside periphery column may behave slightly, but that number is not that significant. Okay, so that's why majority of the column will behave a similar way. That's why we consider unit cell approach and we consider one particular column. So here you can see that we take one particular column and its influence area. Here also one particular column, its influence area. In here also one particular column is influence area. If it is a triangular grid, then influence area will be hexagon. So this is the column and this is the hexagonal influence area. That hexagonal influence area we have to convert it to an equivalent circle. So if the hexagonal and hexagonal, this is the spacing, column to column, S is the spacing. So now that equivalent circle for any form of equivalent area, we can convert to a equivalent diameter. And that equivalent diameter is the D. So equivalent diameter of this equivalent circle. And that is function of S. So if it is triangular grid, equivalent diameter will be 1.05 S. S is the spacing between the column. And if it is a rectangle, then the equivalent area will be also rectangle. Now, if that rectangle we convert it to circle, so basically this is pi d square by 4 equal to a square. So if you do that way from other cases also, so you will get the equivalent diameter. So this is 1.13 S. Similarly, here also it is 1.29 S. For hexagonal grid, it is a triangular equivalent area, and you will get the equivalent diameter. So now here, few terminology, those are very important. So this terminology are stress concentration ratio. What is stress concentration ratio? Now, as I have mentioned that we are inserting stone inside the soil, and stone has a higher stiffness compared to the surrounding soil. So now if I consider a equivalent area or unit cell, within that unit cell, center will be a stiffer material and surrounding will be a weaker material. Now, if I apply a stress, even if it is a UDL, then those stress will not be uniformly taken, equally taken by the soil and the column. Because obviously, stiffer material will take more stress compared to the weaker material. So the stress on the column will be greater than the stress on the surrounding soil, because column has a stiffer material. So that stress concentration ratio is basically stress on column divided by stress on surrounding soil, and it will be always greater than 1. Next one is the area replacement ratio. That means in this equivalent area replacement ratio is area of the column divided by total area of the equivalent area. Okay, so AC is the area of the column and A is the total area. Another is the diameter ratio. Diameter ratio is basically DE divided by DC. What is DE? DE is the equivalent diameter that I have discussed, and DC is the diameter of the column. And obviously, if your spacing is more, if you increase the spacing, then DE value will also increase. So your N value will also increase. So for higher spacing, we have a higher N value. Okay. Okay. So now we'll go to our next part. Now, what are the function of stone columns? So stone columns, basically it serves two functions. One is the drainage, another is the reinforcement. Okay. So till now we are discussing that it has stiffer material, it will increase the stiffness of the overall soil, so load carrying capacity will increase, or it will reduce the settlement because the stiffness of the soil has been increased. The overall stiffness of the soil has been increased because you have inserted stiffer material into the weaker material. So that is reinforcement. That part is okay. If you insert the stone column, its bearing capacity of the soil will increase, settlement will also reduce. But it has another very unique function. What is that function? Well, suppose if you insert stone into the clay, because you know the clay has very less permeability, and stone, because stone has more void ratio, so it has more permeability. So now if you insert the stone into the clay, so your consolidation rate will also increase because it will act as a drainage path. Because suppose if you, without providing stone column, if you want to do the consolidation of a soil, then it will take, say, months or years. Because it's tough, because if it has a 15-meter length of the clay strata, for example, and it has a one-way drainage, so that means it has to travel 15 meters. Then it will have a drainage path, and then it will consolidation will start. But if you provide stone columns, this is large number, you are basically providing drainage path. So now water will get a shorter drainage path to dissipate from that site. So your consolidation will accelerate, and you will get the consolidation with stone column within few days, maybe within few days or months, which you are getting without consolidation by few years. So that is the advantage. So that is another one is the drainage. So for the clay, it will accelerate the consolidation. And for the same purpose, it will do for the sand also. You know that if the sand is loose, saturated, so there is a possibility of liquefaction. So if you don't, all of you know what is liquefaction? Liquefaction is mainly a phenomena for the seismic condition, but sometimes static liquefaction is also occur. But let me right now consider the seismic liquefaction. So during the earthquake loading, your duration of loading is very small. And so that means during the duration of loading, the huge amount of pore pressure is built up within the loose saturated soil. Now, if you provide this technique, stone column, then here also you are providing some drainage path. So that means you can dissipate that excess water pressure which is developed during the earthquake loading through this column. So that means the possibility of the liquefaction will also reduce. Now, what is liquefaction? Now, if the excess water pressure is developed, that means soil will reduces its strength. If soil reduces its strength, that means there is a possibility of the failure of the structure which is constructed or will be constructed on that soil. So if you provide this column technique, that means you can reduce the possibility of the liquefaction, or you can reduce the possibility of the failure of the structure that will be constructed over that site. So that means it accelerates the consolidation, it mitigates the liquefaction for loose sand deposit. So for the clay soil, it will accelerate the consolidation. For liquefaction, it will reduce the possibility. For sandy soil, it will reduce the possibility of the liquefaction. In addition to that, it will increase the bearing capacity as well as it will reduce the settlement. So these are the 4 functions that a stone column can serve. So one by one, I will discuss these 4 functions. Now, first is the acceleration. It will accelerate the consolidation. The first topic that I discussed, that how it will affect on the consolidation. So now, when you are talking about the stone column, now these 3 are the major issues that we deal with the stone column. So first one I have already discussed, that when that means it has a stiffer, it is a stiffer material compared to the surrounding soil. So that means it has a stiffness difference, and that stiffness difference we should incorporate during our design, because this stiffness difference has a advantage. So that advantage we should take care. We should take that advantage. Without stiffness advantage, you can design. Your design will be safe. But if you take that stiffness advantage, then your design will be slightly economical. That's it. But safety-wise, whether you consider the stiffness or not, doesn't matter. But economic. So that's why my suggestion, you should consider that stiffness advantage, because these materials, stone column is stiffer material compared to the soil. Second one, the smear effect. What is smear effect? Suppose when you install this column within the soft soil or the sand, clay or sand, then the surrounding soil will be disturbed, because you are inserting vibroфloat or casing. So surrounding soil will be disturbed. In case of sand, surrounding soil will be densified. So if there is a densification, then the permeability of the soil will reduce. So that means the effectiveness of this system will be reduced. Then the surrounding soil will densify in case of sand. So its stiffness will also increase. But if it is a clay, then surrounding soil clay layer will be disturbed. Its permeability will be reduced. And this strength, this clay structure will be also disturbed. So surrounding clay strength will be also reduced. So it will disturb the permeability of the soil. It will disturb the compressibility or stiffness of the soil. So that effect we cannot neglect. Okay, because stiffness effect is giving a positive. It's given a positive effect in your column performance. So for economical design purpose, you can consider stiffness effect. You should consider the stiffness effect. But for safety purpose, if you don't consider the stiffness effect, your structure will not be fail. It will be safe, because as it has a positive effect, but smear has a negative effect. So if you don't consider that, that means your design may be unsafe. So smear effect you cannot eliminate during your design. And smear effect is a immediate effect. That means when you install the column, this smear effect starts. So it starts from the beginning of the column. Third effect is the clogging. What is clogging? Suppose when we are talking about that, it will act as a drainage path. So that means the fine soil particle will come with the water, because the water is coming from the soil and it will enter the column and then it will go out. So with that water, fine soil particle will also enter into the column, into the soil water. From the water, it will enter into the column and it will basically block the column pores. Okay, and it will reduce the permeability or drainage capacity of the column. So it will reduce the performance of the column. So clogging effect also you cannot neglect. But clogging is not an immediate effect. It's a time-dependent effect or long-term effect. Because clogging will not initiate immediately. It will initiate over the time period. So, but still clogging effect you cannot neglect. but clogging effect you can prevent. So I will discuss how you can prevent the clogging effect. So now if I consider these three effects, so this is a typical degree of consolidation curve. So this x-axis is a time and y-axis is degree of consolidation. Degree of consolidation means if degree of consolidation U is 0, that means no water has been dissipated. Consolidation is not started. And if the degree of consolidation is 1 or 100%, that means all the water has been dissipated, full consolidation takes place. So that is the significance of this curve. So you can see as time progresses, your degree of consolidation also increases and goes towards the full consolidation or 90% degree of consolidation. So you can see as NS value, NS is basically the stress concentration ratio as I discussed. Now as your stiffness increases, then if your material become more stiff, then stress concentration ratio will also increase, because as material become more stiff, more stress will come into the column, less stress will come into the soil. So stress concentration ratio will increase. You can see as stress concentration ratio increases, then your consolidation rate will become more faster. So that means stiffness has a positive effect. So that means as your material is more stiff, then your rate of consolidation will increase. That means the consolidation rate will be more faster. Okay, so that is the significance of this curve. And then as you can see, as expected, as diameter ratio is more, that means the spacing is more, that means it will take more time to consolidate. Because as the spacing more, that means your drainage path will be also more, it will take more time to consolidate. Now the second one is the smear effect. Because stiffness has a positive effect, it will accelerate the rate of consolidation or it will reduce the settlement of the structure. The smear effect, you can see this is the column, this is the smear or disturbed zone, this is the undisturbed zone. Okay. Now, as I mentioned, during this installation process, the permeability and the stiffness of the soil will change. Now, the question is how it will change, in what form. So, in some laboratory tests, they have observed what they have done in the laboratory. They have taken some soil sample after installation, and then they do the permeability test, and there they find that this reduction is in parabolic form. Okay, it is not sudden, it is not linear, it is parabolic. Okay, so now considering this idea, what we have done, we have taken three different variations. So we have taken a sudden decrease of the permeability and the compressibility. Okay, so compressibility will increase because stiffness will decrease, the compressibility will increase. Because compressibility is inverse to the stiffness. If your stiffness increases, compressibility will decrease. If your stiffness decreases, compressibility will increase. Okay, so here you can see the permeability. There is a sudden decrease we have considered in the disturbed zone. Then we have considered a linear decay, and then we have considered a parabolic decay. Because in the test we have observed there is a parabolic decay. And then next question will come, the how much area will be affected. Generally, it is observed that 2 to 2.5 times of diameter of the column zone can be affected due to the installation. But that also depends on how you are installing the column and which type of soil. So which type of soil, how you are installing your column. Depending upon that, your zone of disturbance will be decided. And then you can see, but here this zone of disturbance, there is a sudden drop, linear and parabolic. Now we can see, we compare these our analytical result with the field test data, and we observe the parabolic variation is giving most appropriate variation in terms of field data observation. So parabolic variation is matching well with the field data. So we can conclude that in the smear zone, the variation or reduction of the permeability or the variation of the compressibility is parabolic in nature. Okay. So now what we have done, we have taken, so most of the studies, they have considered only the reduction of the permeability, because we also consider the reduction of the permeability as well as increase of the compressibility or reduction of the strength, both. I mean, compressibility effect as well as permeability effect we have considered. To see whether how much effect of compressibility has on the degree of consolidation. Then we observe that when the permeability is decreased by 10 times, that means your degree of consolidation to achieve. So suppose you want to achieve a certain degree of consolidation, here 90% degree of consolidation. So initially, if you don't consider the smear effect, it is say 30 days. Now, if you consider the smear effect, then that 30 days will increase to 60 days. So that means if you consider the smear effect, only the permeability, then it will increase by 2 times. The time will increase. So that's why I am repeatedly telling that when you design this column, you have to consider the smear effect. Okay, so because it can increase the time up to 2 times. But whereas if you consider the compressibility only, then that increment is only 20%. So what is the conclusion from this study? That permeability consideration, permeability reduction, we cannot eliminate in the smear zone at any cost, because it can increase the time by 2 times to achieve a particular degree of consolidation. But for compressibility, it is only 1.2 times or 20%. So you can neglect that, because to simplify your analysis or simplify your design. So that means that is the conclusion. Compressibility you may neglect, but permeability in the smear zone you cannot neglect, because it has a significant effect over the consolidation. Next one is the clogging. So now we have done the clogging, and we can see that this clogging can increase the time to achieve a particular degree of consolidation up to 45%. So that means clogging can increase the time also up to 45%. So it can clog these voids. So that means clogging cannot be eliminated, but clogging can be prevented. How clogging can be prevented? So now if you encase the stone column by geotextile, geotextile is a polymeric material, so that you encase around the stone column. And if you choose this geotextile with proper opening size, so that thing I am not discussing here, because there is another topic, that how to design a filtration to prevent the clogging for the stone column. So that is another topic. So that's why I am not discussing in detail in that topic, because there are so many other things will come into picture. But now I'm just giving the information. If you want to prevent the clogging, then you have to cover this stone column by the geotextile, and you have to choose the geotextile in proper way, by proper opening size, so that the idea is that you cannot fully prevent the blocks, because water has to pass. Now, if you choose a geotextile where permeability you are not allowing any, there is no pore, it will not work. So there should be pores, and you have to select those pores properly, so that you can prevent the fine particles migration, but at the same time you have to allow the water to flow into the column. Okay, so that means if you can prevent it. So now the question is, there are 3 things that I have discussed: stiffness, clogging, and smear. Stiffness, I recommend for the economic design you consider, but if you don't consider that, your design will not be fail. But smear, it is mandatory to consider, specifically the permeability effect. Compressibility you can neglect, but the clogging you can prevent it by providing geotextile. If you don't provide the geotextile, then the clogging also you have to consider during design, because as I mentioned, there can be a time delay by up to 50% if you consider the clogging. Now this is the encased column. Now how to design stone column improved ground, considering the in terms of your consolidation. In terms of consolidation, how you can design that. So there are design charts are available, design equations are available. You can go to Han and E paper. So their charts are available, equations are available. You can use the equations because these charts are developed from the equation only. So now if you have the soil properties, what are the properties you need? So you need the coefficient of consolidation for the soil, vertical as well as horizontal. If you know this property, and if you have a target time, so okay, I will design it for 60 days. Okay, so that is the time. D is the equivalent diameter that I've discussed, which is function of S. So you have this TR value, and in terms of NS is what? Stress concentration ratio. That means the stiffness effect is being incorporated here. So that means in this chart, if you use this chart, here stiffness effect is being incorporated. So stiffness effect is there. So from this chart, for a particular N value also I have discussed, that is dE by dC. So for a N value, what would be the degree of consolidation that you will get from this chart? Now, if that degree of consolidation is your targeted degree of consolidation, then fine. Otherwise, you have to redesign it unless you achieve that target degree of consolidation. So first chart is giving you the radial consolidation, and second chart is giving you the vertical consolidation. Now, what is radial consolidation? What is vertical consolidation? Now, when we are talking about if I don't give any column, then the column and there is only one-way drainage, then there will be only vertical flow of water, because there is no scope of radial flow where the water will go in radial direction. Only vertical direction it will go up and then it will dissipate, because above the column we have provided the sand drainage. Okay, sand blanket, so it will go up in the sand blanket, it will act as a drainage path, so it will go ahead. Now, if I provide the stone column, then the water will go in the radially also, because if it will go in the radial direction, you can see if it is go in the radial direction, this radial direction, it will enter into the column. Okay, and radial consolidation is much faster than the vertical consolidation. Why? There is two reasons. First reason is the radial permeability is higher than the vertical permeability of the soil. And if you consider in terms of drainage path, that radial drainage path is smaller than the vertical drainage path. For example, vertical drainage path is 20 meter or 15 meter. If you have a 15 meters clay strata, where a radial drainage path may be 1 meter or 1.5 meter, maybe less than that. So that's why radial drainage is faster than the vertical drainage. But it doesn't mean that when there will be a radial drainage, there will not be any vertical drainage. So there will be a radial drainage as well as the vertical drainage, but the contribution from the radial drainage is more compared to the vertical drainage. So this is the equation. You can get the overall contribution. UR is the degree of consolidation for radial drainage. UV is the degree of consolidation for the vertical drainage. So this is the equation. So it is observed depending upon the soil type that your 75 to 80%, maybe 85% will be your radial drainage, and 10 to 15%, maybe less than that also, for the vertical drainage contribution for a particular time. Okay, so this way you can design the stone column. That means the spacing and diameter, and length. Length means how much. Suppose you have a clay strata. and you want to do the consolidation. So you know how much the clay strata is there, that poor clay strata. So you have to provide your column up to that depth. Okay, so this way we can go for the length, spacing, and diameter. And what are the properties you need? You need the soil properties, and you need the stiffness of the column and the stiffness of the soil also. And obviously now another thing that I have mentioned, that in these design charts, the smear effect, clogging effect, these are not considered. So these charts you have to use with caution. What caution? That if there is a smear effect, as I discussed, then that time will be increased by 2 times. For example, if your target design is say 60 days, within 60 days, you want to get the full consolidation. And if you want to use this chart, actually you design it for 30 days. Then if you consider the permeable smear effect, then that 30 days will go to 60 days. So that 60 days is your actual target design time. So that means if you design it for 60 days, now if the smear effect comes into picture, then it will take more than 100 or 120 days. So now if your design target days is 30 or 60, then you have to design it considering lower time, so that because as I have discussed, there will be 2 times time delay. So when the smear effect will come into picture, then you can achieve your target day, where you will get the full consolidation or full settlement. Okay. So, and if you prevent the clogging, then by using the geotextile, then you have to choose the proper geotextile. Then this clogging effect don't need to consider, because if you can fully prevent the clogging. But if you have not considered the geotextile, then clogging time delay also you have to incorporate here. That means that is the up to 40 to 50% time delay. So that also you have to incorporate here. That means a time delay due to smear and a time delay due to clogging. If you consider these all effects, then only you will get a proper design time. Otherwise, your target design time you will never achieve. Your required time will be more compared to the target design time. Okay. So now, as I discussed, I will finish it by half an hour. 1 hour. So I have a few minutes, 15-20 minutes more. So I can discuss the liquefaction part also, because that is these two are the major things. So now the liquefaction part, as I mentioned, that due to liquefaction, soil loses its strength, and this is the outcome. So if you look at this building, there is no that much of structural failure. This is failure of the liquefaction. That means the failure of the foundation. Soil loses its strength, so this is the foundation failure. Now, how to prevent that? Okay, so there are. It is not that only stone column is the option. No, you have a number of ground improvement techniques are available by which you can mitigate the liquefaction, but each method has their own advantages, disadvantages, and based on your requirement, you have to select the proper ground improvement techniques. But stone column is one of such ground improvement techniques. So I will discuss the stone column. Again, here also these 3 effects I have to discuss, that the stiffness, smear, and the clogging. So here, if I see this graph, what is this graph? Let me explain this graph. This x-axis is the T. T is the duration of earthquake. And y-axis is the excess pore water pressure. It is in non-dimensional form. So you can see that y at 1, it is maximum. And after that, it start decreasing. Because at 1, this T is the non-dimensional time. So at 1, it is the end of earthquake. So you can see, so from the starting, during the earthquake, your pore pressure will generate, and after that, it will dissipate. Okay, so that is the significance of this curve. And you can see that again also the stiffness has the positive effect. So you can see that your pore pressure can be decreased by 20 to 60% due to stiffness effect. So that means there is a roughly on average 40 to 50% decrease of the excess pore water pressure if you consider the stiffness effect. So again, as it is a positive effect, so it is up to you whether you will consider it or not during your design. But my recommendation, you should consider. Okay. Now we have discussed the so many permutation combination, and then we find average again 30 to 40% excess pore pressure will increase if you consider the smear effect. So that means smear effect, stiffness effect decreasing the pore water pressure, smear effect increasing. That means smear effect as a negative effect. We cannot eliminate that. And then there is a clogging. So clogging as a in the consolidation part, clogging is a very time-dependent phenomenon. So clogging starts when the consolidation starts. After some time, the clogging will start. But earthquake is very small duration, no? Say 50 seconds or maybe less than that. So within that period, how the clogging, what is the significance of the clogging? The clogging has not that much significant during the earthquake, because during the earthquake your dissipation of the pore water pressure, although dissipation and generation both will act at the same time, but during the earthquake your generation of the pore water pressure is more significant compared to the dissipation. So you can see the clogging doesn't have any significant effect during the earthquake, but after the earthquake it has, the clogging will start when the pore pressure will try to dissipate. Okay, so that means what is the meaning? That means that you have provided the stone column, and during the liquefaction it will start dissipate the water. During that time it will delay that dissipation of the water. So after the earthquake it has the effect, clogging has the effect, but that is true for the first earthquake. But the second earthquake, because during the first earthquake, after the earthquake, your clogging has been occurred. Now under these conditions, if your second earthquake comes, now that is a significant effect on your design, even during earthquake, and it may fail. Your total system may fail because you have a now the clogging will give the effect, start the effect immediately during the earthquake also, because the pores are being clogged after the first earthquake. So that means here also clogging you cannot eliminate, you have to prevent it, okay, by providing the geotextile. So, and now the question is that there is a term called plug burst. What is plug burst? That means that your fine particles are entering into the column pores. Okay, and there is an optimum condition that is called optimum clogging. Under that clogging, if again a thrust of water comes, then this clog particle breaks. Okay, so that means again water starts flowing after optimum plug. This is called plug burst. And then again it will plug after certain time. Again the clogging will take place. Again there will be optimum clogging. Again there will be plug burst. So now the question is, what is the optimum clogging for stone column? When it will plug burst? These information are yet to be known. Okay, because as I mentioned, these are very advanced studies that we are going. So I don't have any idea. That's why maybe in future we may identify what is the optimum clogging for stone column, when there will be plug burst. Right now, it is cumulative. No? So first earthquake, there will be clogging. Second earthquake, more clogging. Third earthquake, another more clogging. Actually, it will not happen like this. There will be optimum clogging. There will be a plug burst. Now again, it will start from zero, the clogging. But this phenomena is still yet to be known. So even I don't have any idea. So right now, that's why we have discussed about the second earthquake only. And our recommendation that you prevent clogging by providing geotextile. Otherwise, there is a possible of failure of the system. Okay, so here also we have the design charts that we have developed, and here also the similar way we have to decide the diameter and we have to decide the spacing of the column, and here stiffness effect is incorporated in this chart. So I am not discussing this chart in detail. These charts are available in the literature. Just so that means here the stiffness effect is there. Ultimately, we have to determine the diameter and the spacing, and length will be up to the liquefiable zone. And here, what are the properties that are required? The permeability of the column, then permeability of the soil, compressibility of the column, compressibility of the soil, then number of cycles required to cause the liquefaction, and number of cycles that will generate during an earthquake. So these, and the duration of the earthquake, these properties are required. Okay, and unit weight of water is obviously required. So now again remember that in these charts, this is the smear effect and the compressibility and the clogging effect is not considered. So when you use this chart, you have to keep in mind that smear effect has a negative effect, and clogging, if you prevent it, then you can neglect. So again, your smear effect also you have to keep in mind, because for example, here, if you want to design it for a Umax value of 0.6, okay, but if there is a smear effect, then it will go beyond 0.6, but your target design is 0.6. So that means if you want to incorporate the smear effect, you design it for 0.4 or 0.5, because there will be 30 to 40% increase of the Umax. So if there is a 30% or 40%, even 60% increase of the Umax, then that will go to your target Umax 0.6. Okay. So now I will go to the third thing. I've discussed the consolidation, then the settlement, then the liquefaction. Now it is the bearing capacity and the settlement. So bearing capacity, there are a number of ways you can determine the load carrying capacity of a single column, but I have discussed only the methods which is given by our code, this IS code 15284 part 1 2003. They have given an equation. I'm not discussing the detail on the equation. I'm just discussing the mechanism. What are the four way you are getting the resistance? So there are three parts. Okay, this is part 1, this is part 2, this is part 3. So the three way we can get the resistance. Part 1 is when you apply the load only the column, this column will try to bulge. So the surrounding soil will give you the resistance. So that is the resistance from the part 1. And again, now if you provide the granular part or foundation, and that you will provide beyond the column also, as I already discussed, if you apply the stress beyond the column also, that stress will act on the soil, and that stress which is acting on the soil will give a resistance to the column. So that is the second part. And third part is the stress carrying capacity of the soil itself. Okay, so if you add these three, then you will get the load carrying capacity of a unit cell zone of the stone column. Then you have to apply the factor of safety. So this way you can determine. Similarly for the settlement also, there is a term settlement reduction factor. So this is called settlement reduction factor. So what is that? You have equation also by which you can determine settlement reduction factor. You have charts also given by different researchers. From there also you can get a settlement reduction factor. So once you get the settlement reduction factor, now you have a settlement of the untreated soil. Now if you multiply with the settlement reduction factor, then you will get the settlement of the treated soil. So you can say that settlement reduction factor can vary 0.1 to 0.8. So that means there is a huge settlement reduction, and that depends on the area ratio. So if DEDC is very less, 1 point something, that means your most of the zone influence zone is replaced by stone. So obviously settlement will be less. As your NS value, as your AS value will decrease, I mean area ratio will decrease, you will get higher settlement. As your area ratio increases or DE by DC increases, then you will get, DE by DC decreases. DE by DC decrease means area ratio will increase. Okay, DE by DC decrease means your most of the area of the influence zone is replaced by stone. So as DE by DC decreases or area ratio increases, your settlement will be less. As DE by DC increases or area ratio decreases, there will be more settlement. So this way you can discuss the settlement also, determine the settlement also. This technique is also discussed in the IS code. So that means I have discussed all 4 functions. That means consolidation, mitigation to liquefaction, bearing capacity, and settlement. So now some application areas. Okay, so I will take hardly 5 to 10 minutes. After that, I will finish that. So there is a, now till now that I have discussed, those are all ordinary stone column. So ordinary stone column, the majority of the stone column failure reason is bulging. Now, one way we can, now if I provide the reinforcement around the column, so one way I have discussed, if I provide the reinforcement geotextile around the column, that means it can prevent the clogging. Now, if I provide the geogrid or stiffer reinforcement, it can prevent the bulging also. So that means if you prevent the bulging, load carrying capacity will increase. So it is called encased stone column. So this is the encased stone column. And there is another type of stone column also. Let's go laminated stone column. Laminated stone column means this reinforcement circular reinforcement sheet are inserted into the column in certain layers. But I never worked on that thing because I have a doubt how that can be placed exactly in the field. But encased stone column is a very good idea that you can use to prevent the clogging as well as the bulging. There is another way. So you can increase the load carrying capacity of the column. That we are providing the sand blank over the stone column. Now, inside the sand blank, if I provide the reinforcement, then also load carrying capacity will increase. Let's see that. So suppose this car is for only clay bed. This is clay bed with stone column. This is clay bed with stone column with granular pad. And this is clay bed with stone column with granular pad with reinforcement layer. So you can see the granular pad also increasing the bearing capacity. And if I provide the reinforcement within the granular pad, that will also increase the bearing capacity. Okay. So now finally, there is, if you provide encasement or the reinforcement in the granular path, then your bulging will go down. Because as I discussed for ordinary stone column, bulging depth is generally 2 to 3 D. Generally for 1.5 to 2 maximum bulging will occur. So you can say this is ordinary stone column. Bulging depth is 1.2 D. So this is the laboratory test. And here it is 2.2 D. If I provide a sand pad, if I provide a sand pad here, and if I provide a reinforcement within the sand pad, it will go further down. So these bulging terms that we have discussed now, that is for original stone column or normal stone column. But for the encased or the reinforced stone column, the bulging depth will go further down. Okay, so now some application area. So this is one application area, that is your stone column supported embankment. So this is very much useful for roadway and railway. So this is one application area. So when, just to give an idea that when you analyze this type of structure, it is not that suppose these embankment load will gamma into H, we multiply the stress and then we check whether that stress this column can carry or not. No, there will be few mechanisms. So one of such mechanism is soil arching. Soil arching means that because this soil is very soft, this is very stiff material. So this soil will deform more compared to this stiffer material. So the soil above within this embankment, granular soil, they will deform more compared to the soil above this column. So there will be a shear zone. So along the shear zone, stress will be transferred to the column. So that is called soil arching. So if you provide reinforcement, so remember that there will be three mechanisms by which stress will be transferred to the column. So what are those three mechanisms? I have already discussed that stiffness difference. Even if you provide it below a raft, there is no soil arching. But again, the stiffer material will take more load compared to the weaker material. So column will take more load because of it is a stiffer material compared to the soil. Another is the soil arching. Because of soil arching, stresses will transfer to the column. Another is this reinforcement. This reinforcement will also transfer the stresses from weaker layer zone to stiffer zone. It will help to transfer. So these three mechanism, the stresses will transfer to the column. So you can see the column will take more stress compared to the soil. So when this type of structure, when you check the bearing capacity, you have to check the bearing capacity individually to the column, individually to the soil, because stress is not same over the column as well as the soil. So this is some experimental picture. I can show you the evidence of the soil arching, because this portion is void. There is no support. Still, these sands or granular material, they are not falling because these stresses are already transferred to the rigid material or rigid part. So it can stand. This is called the soil arching. And another one, that when we apply the stone column in the embankment, because this embankment is a long, length is very high. A stone column is a circle. So if I do the analysis, so we have to also convert the stone column into a strip. Otherwise, how I can do 2D analysis? I can do 3D analysis, but if you want to do a 2D analysis, then you have to convert it. So there are two conversion techniques. One is you keep the dimension of the column same, the diameter of the column and trench width same, but you change the properties of the column and the soil. Another thing is that you keep the properties of the soil and column same, but reduce the dimension. That means your trench width will be lower than the diameter of the column. And second method is most appropriate method compared to the first. Similarly, another application area is the below the tank foundation. So there also, when you do the analysis, because this is the column is in brief, but it is a circular tank, so it is axisymmetric kind of analysis. So there also, if you do the 3D analysis, fine. Otherwise, if you do axisymmetric analysis, then we have to convert this thing with concentric circle. Okay, all the columns, these are the columns. So these columns are concentric circle to make a axisymmetric condition. Then we do the analysis. So these are some, so I have discussed all the application areas and then few application areas and how you can proceed for the analysis. So mainly we have discussed the consolidation, liquefaction, these two parts and some application areas. So that's it. This is the end from my side. And if you have some question, we can take few such questions. Thank you. Thank you very much.
Sir, they can unmute themselves and they can ask the questions now.
Yeah.
And in the chat box also, there are some questions, sir.
So the chat box questions, okay, I can
read out. If you want, I can help you.
Okay, some common question that if I go for the pile foundation, yeah, I have given some question in the chat box. That one question, what is the cost effectiveness? If I go for the pile, and if I go for the say raft or with column. So one site we have done, but that is also site specific. So we can reduce the cost by 50%. So that is so cost effective. 2 times to 2.5 times also. Okay, so any question?
Sir, my name is Dr. Ramesh. I'm also professor and as well as doing a lot of consultancy over here in Bangalore. Just I have a small question that in very highly plastic clays, okay,
Yes.
within a high groundwater table is there, then I need to increase the safe bearing pressure. But the minimum depth of excavation and all that, it will go up to 3 meters and all that. So from there, again, making a stone column or the sand rinds will becomes very difficult. So in such cases, actually the pile foundations we prefer is very economical there. Comparatively,
yeah,
with
as I
respect
mentioned, it is not always that I have stone column, I have to use it always. No?
okay,
It is site specific, definitely. Sometimes even pile foundation is the better solution than the
stone column.
Yes, because sometimes it is very difficult to construct the stone column. You cannot construct the stone column if the site condition is so poor. Okay, even the soil is even very soft soil. Even you have some amount of strength in the soil, because otherwise your column will not stand, because column is getting resistance from the soil. So if you have such kind of soil, you don't have the other option going to pipe. Yeah.
Okay. Now that was in a majorly in some of the sites in Bangalore. We tried with stone columns and as well as sand rinds, but it is not at all acting properly.
I mean, physically you can, theoretically you can, but when you go for the construction side, then only face the difficulties. So depending upon if soil, suppose for example in the lab we have seen that if the soil cohesion value is less than 10 kPa, you cannot construct a column. Even,
yeah, absolutely, sir.
Even side also, that value is around 7-8 kPa. If you have a strength value is less than that, you cannot construct column.
Yes, sir.
So in such case, you have to go for other things.
Thank you, sir, for the nice information on that.
Yeah.
Good afternoon, sir. This is Vivek Singh. I'm from Lucknow. I'm basically into road making, and I have seen one problem, especially in reinforced earth construction. You must have be aware that there are a lot of failures happening all over India because of most of the reason. I mean, one of the biggest reason is the material used in the reinforced earth wall, and that is they don't use the sea-less soil, and which is recommended in the codes and all. My question is that, to my understanding, the requirement of cohesionless soil is the poor drainage of cohesive soils.
Mostly.
Can we use such technique to improve the drainage of those soils in the RE walls, and so that our range of usable soil increases and such failures do not happen?
So now, if in such cases we can provide the weave holes. So weave holes, are you providing that holes within the because that is for your normal retaining wall?
It's not the weave hole. It's a drainage layer provided along the sides of the panels.
Side of the wall. Yeah.
Yeah. That is on the edges.
On the edges. Yeah. So, but
I mean, still.
RE wall, reinforced retaining wall, we have not provided drainage path. Whatever
not reinforced retaining walls, sir. I am talking about reinforced earth walls.
Reinforced earth wall. I mean, that is the RE wall that we were talking about.
Yeah.
So generally, in the normal retaining wall, you can provide the drainage path. You can, if you have a C5 soil, you can provide some drainage.
There is weep holes and
weep holes and other things. But for reinforced retaining wall, we have not done so far this type of thing. Their only option is you have to go for the as much as cohesionless soil.
It has not been tried there. till now.
Yeah. But maybe future we may also think that thing also, because sometimes getting questionless soil in the site is very difficult. We have to go for
we are making roads, and roads go.
We have to go for the local soil, and bringing good quality soil is very costly.
Very costly, and sometimes it doesn't happen because of that. There are contractors who do not pay heed to it.
Also, it is the mind of the engineers. So people are working that. Hopefully, you will get some solution very soon.
Thank you.
Any questions from the participants?
I think
Sanat, see the chat box.
one question is there. Okay, sir has already asked. Okay, those questions asked, and he has also answered for those things.
Now there is another more question in the chat box that let me read that.
I have a question in chat box about laminated column. What is the material used for the lamination?
Geosynthetic you can use, geogrid.
Okay, geogrid.
Now, generally geogrid. Nowadays, people are using jute geogrid also, which is cost effective but not durable. You have to make it durable. And mainly it's a geogrid. I mean, that is in horizontal layer form. But I don't know how effective it is because when you do it, because I personally use encasement rather than lamination. Because laminated, the problem is that when you do the vibration within the, because your vibroflow will vibrate within the column, you have to compact the column. And
I find its application, as my earlier question was, in reinforced earth wall, because there I have to build up the embankment with the drain.
Yeah.
There maybe this lamination thing will work very well.
In that case,
better constructability.
That case works. But you have to, suppose in the stone column, what will happen? That you have to vibrate your instrument within the stone. And if you have the reinforcement, there is a possibility that your reinforcement may damage.
Yes. There it may be. Yes.
So that's why rather than going encasement is very easier in construction point of view. But if you have a short column, then you can do it, this lamination thing. And all this lamination, encasement in terms of bearing capacity is done within the bulging depth only, that's 6D or 5D for in terms of bearing capacity. But if you go for a clogging purpose, then it is recommended you go for full, because you have to prevent the clogging for whole stone column.
Sir, one more question is there.
Yes. What is that question?
Are there any real projects that last?
There are so many projects in geosynthetic and stone columns in India also. Okay. In
yes, sir.
even the photographs that I have shown, that is a photograph of a real project.
Yeah. I think no more questions.
Yeah. Thank you, Professor, for joining, and you have given the design to applications with respect to ground improvement techniques using a stone column method. It is very interesting, and we are able to see what are the parameters to be considered while designing the stone column. And you have touched upon the application part also, because earthen dams is an important concept. I am also a water resource engineer, and I'm able to see some of the applications of the stone column. Thank you, Professor, for accepting our invitation and spending your valuable time with us. And you have shared all your the information related to stone column. I hope that all my participants benefited with this webinar. Now I request Dr. Suravi Pal, the coordinator of the program. The professor is today giving because of the Suravi Pal, and she is also a student of Kousik sir. Now I request Dr. Suravi, please conclude and propose the vote of thanks.
Yes, sir. On behalf of Nagarjuna College of Engineering and Technology, I would like to thank our distinguished guest and speaker, Dr. Kousik Deb, for making excellent presentation and making this seminar interesting and meaningful. I would also like to thank our principal, Dr. Jitendra Mungara, and our beloved HOD, Dr. Venkatesh Babu DL, for his constant support and encouragement. I would also like to thank Professor Sanath Kumar for smooth conduction of this session and all technical assistance. On behalf of Nagarjuna College of Engineering and Technology, my heartfelt thanks to all the participants of the session. Thank you all.
Okay, thank you, Dr. Paul.
Yeah. Thank you, Professor.
Thank
Once
you,
again.
sir.
Thank you. Thank you.
Thank you, sir.
Okay.
Sir,
Bye-bye.
shall I end the meeting?
Yeah.
Okay, bye-bye, sir. Take care.
Bye.
Take care.
Thank you, sir.
Thank you.
Bye-bye.